We might have seen several examples like a needle kept on the surface of water, it's remaining flat on the surface, and we might have seen the insects walking over the liquid surface or water surface, especially in the wells and all. You might have seen small insects walking over the surface. So it is due to a property of the water or any liquid by which its surface act as a stretched elastic membrane, and the property of that liquid is called as surface tension. So surface tension can be defined as the property of matter by virtue of which a free surface of the liquid behaves like a stretched elastic membrane having contractive tendency. So it tries to minimize its surface area. That's what we mean by contractive tendency. Now, to explain surface tension in detail, we consider molecules within the liquid. So the liquid molecules, among the liquid molecules, there will be force of attraction. We consider three molecules as shown, A, B and C. As we see, the molecule A is well inside the liquid. So that molecule is attracted equally by the nearby molecules to all sides. So when we consider the net force of attraction on that particular molecule, that net force will be equal to 0. When we come to the molecule B, in the case of that molecule also, even though it is nearer to the surface, for that molecule also the net force will be equal to 0. But in the case of molecule C, when we consider the molecule is attracted by the other water molecules in the downward direction, but in the upward direction it's not there. That means the molecules on the surface of the liquid, it experiences a net downward force. So a net downward pull is there on the molecules which are there on the surface. It's because of this net downward pull, the molecules or the surface itself act as a stretched elastic membrane. So we can say that the molecules on a liquid surface, they have some extra energy in comparison to the molecules in the interior. It is actually due to this extra energy for the molecules on the surface of the liquid act as a stretched elastic membrane. So surface tension, it can be defined as force per unit length, or it can also be defined as surface energy per unit area. So it is, the surface tension is force per unit length acting in the plane of the interface between the plane of the liquid and any other surface. It means the interface. So when we keep a liquid in an open vessel, the interface is between the liquid and air. So at the interface between liquid and air, we define this surface tension. So actually that is the liquid surface. So it is the force per unit length of the liquid surface. That's what. So it can also be defined as surface energy per unit area. So the value of surface tension, it depends on temperature, and surface tension of a liquid usually it decreases with rise in temperature. So this table shows the surface tension of different liquids. Now we spoke in terms of surface energy. Surface tension we define in terms of surface energy, and actually what is this surface energy? Surface energy, it is the energy required to increase the area of the surface of the liquid by unit T. That's what we mean by surface energy. So energy required to increase the surface area of a liquid by unit T. By unit T means by 1 meter square. That's what we mean. That energy required is called surface energy. And this surface energy per unit area is the same as surface tension. That is why initially we defined surface tension like that. Surface energy per unit area, or surface energy as such, that energy required to increase the surface area by unit T, that is the same as surface tension. So surface tension and surface energy are similar dimensional terms, and they are the same. When we speak about the effect of surface tension, it is due to surface tension, the liquid surface, they act as elastic membranes, stretched elastic membranes. And it is due to this surface tension, the liquid surface has a tendency to reduce the surface area. And example for these two effects, we can see many things. That means when we immerse a brush into water, we can see that the bristles of the brush, they are far apart. That means they do not cling together when the brush bristles are inside water. But when we take the bristles outside water, we can see that the bristles, they cling to each other. It's because of the surface tension which for the liquid which is there inside the bristles. That means when we immerse it in and take it out, there is a layer of water formed between the bristles, and this water has a tendency to minimize its surface area, because of which its shapes becomes like that. And it is due to that surface tension, these bristles, they cling to each other, because the layer of water between the bristles tries to minimize the surface area because of surface tension. Similarly, all the liquid drops, the shape of liquid drop, it is spherical. No water drop or any other liquid drop you can see in any other shape, because for a given volume, the surface area is minimum for a sphere. That is why the liquid drop, it takes spherical shape, okay, to minimize the surface area, and it is because of the property of surface tension. So we can have many examples for this surface tension. Now we have an expression for surface tension, or it is the same as the proof for the fact that surface tension is the same as surface energy. Now we consider a rectangular frame with a movable side. So in this frame, this is the movable side. This is the movable side. It can be moved, and other sides are fixed. And this rectangular frame, it is dipped in a soap solution, we can consider, so that we'll have a film of soap formed like this. This is a film of soap solution, we can say. So we have a liquid film in the rectangular frame. So the shape of the film, soap film, it is rectangular in shape. Now we can see that we are applying a force. Okay, so on this movable part, force is acting, because here we have an interface on this side. We have an interface between the liquid and the air. So there is surface tension, and because of that force only, it is acting as a stretched elastic membrane. Now we are trying to increase this surface area by moving that movable side. So for that, we are moving that movable side through a small distance d. The bar is moved through a small distance d. So we can say that the area of the surface increases. Okay, so we know surface energy is defined as the energy required to increase the surface area of the liquid by unity. Now suppose S stands for surface energy. So to increase the area, that means we are moving the movable side through a distance d. So when it is moved like this, the liquid surface area is increasing. There is an increase in area, and the amount through which the area has increased on one surface, it is d into L, because it is rectangular in shape. This side is L, this side is L. This side is L and this side is D. So L into D is the increase in area. And the liquid, that film has got two surfaces. So because of that, the total increase in area we can write as 2dl, because of the two surfaces for the soap film or the liquid film which we are considering. So the increase in area, we can say that it is 2dl. And we assumed S to be the surface energy. The surface energy is S. So the energy required to increase, or energy required to move the bar or that movable side, it is S into 2dl. So we got an expression for energy required, that is to move that movable side, it is S into 2dl, because S is energy required per unit area and that into 2dl. 2dl is the increase in area. So we have S into 2dl as the required energy. Now we know the film, it is moved through a distance d. Now the force, the applied force, suppose it is F. So how much force we need to apply? Because of surface tension, it is experiencing a force inwards. Because of surface tension, it is experiencing a force in this direction. The liquid surface, it experiences a net inward force, we know, and opposite to that force only we need to apply a force. So the applied force is in this direction. And how much should be that applied force? That applied force, it should be at least equal to the force due to surface tension. So here we assume the applied force to be F. Now the distance through which the movable side is moved is d. So displacement by the application of force F, it is d. So the work done is F into d. So we have the work done by the applied force as F into d, and this work done is stored as that increase in energy which we said, that is S into 2dl. So we can write F into d is equal to S into 2dl. So we have S is equal to Fd divided by 2dl, or dd get cancelled, and we have F by 2l. And when we look at F by 2L, F is the force applied, and that is the same as the force acting on the liquid surface by the property of surface tension. That by 2L, that 2L comes as the total distance or total length, we can say. So surface tension, it is the force per unit length. So we got S is equal to F by 2L. S we know it is surface energy, and F by 2L. F by 2L is force per unit length. That force per unit length, it is surface tension. So we have proved that surface energy is numerically equal to surface tension. And it is by this equation we define surface tension as the force acting on unit length of an imaginary line drawn on the surface of a liquid. That way also we can define surface tension. Force acting on unit length of a line, imaginary line drawn on the liquid surface. In that way also we can define surface tension.